with the recording. Okay. Okay, now it's okay. Okay, so
Now Cisco has. Oh,
okay.
I hear my voice.
Yes, you need to mute. Maybe better if you mute the microphone for the people. Okay, now I can start. So thank you all the participants being here. We have the satellite working group of the INGR initiative. We have a few slides and I'm just providing an overview of the activity carried out last year. We basically have provided a report that has been presented at the Future Network Forum 2025. This is the 5th edition of the report that probably will be, because the process is complex, but it will be made available via IEEE Explore. We organized many, basically a couple of webinars in 2025 with a good attendance, good number of participants, and typically we meet every 2 weeks, and many times like this we have a technical presentation. Of course, we have to be grateful to the activity of the participants who have worked a lot. This is the 5th edition. Is in any case a preliminary version is available on the INGR website. So basically, it is already published, but not yet on IEEE Explore. And then this year we will focus on evolving our work on the satellite and future evolution to cope with IMT 2030 requirements in terms of usages and new capabilities. So our task this year is to align with IMT 2030 and to take into account these two wheels to investigate further on critical aspects, in particular sustainability, coverage, efficiency, and security, and the like. So I think I now stop presenting our group. We have also a joint paper that is almost ready and to be submitted. So we are very active. So then I think now I can move to the technical presentation of today. We are very happy to have here the speaker, Thomas Coughlin, past IEEE President 2024. He will provide a presentation on memories of space, or the industrialization of space depends upon digital storage and memory technology. So we are very honored and proud to have your talk given today to our group. Thank you so much.
Well, thank you very much. And thanks for the opportunity. Like I was telling folks at the beginning here, I'm actually I live in Silicon Valley, I live in San Jose, and I'm giving a version of this talk to a local group live in San Jose. It's a consultants network, Silicon Valley, next week. So you guys are my practice run on this. And also, I want to note too, and there might be some future collaboration possibilities here, is there's a new, and I'm going to mention it at the end of my talk, but there's an emerging space tech initiative in the IEEE Future Directions Committee. And so I think it probably makes sense for there to be some interaction with you folks on that, especially considering your interest and the connections to doing things in outer space. So I'm a storage and memory guy. That's my background. And so I'm going to focus on data centers in space and, development of outer space in general, and, memory technologies to make that possible, memory and storage technologies to make that possible, what's been going on, what are the possibilities. So talk first about some of the challenges and opportunities. You folks maybe know a lot about these, about data centers in space, and about all the everybody and their brother seems to be hopping on top of this topic right now. Google, NVIDIA, even the Amazon folks. It's SpaceX, of course. So there's a lot of really interesting things going on in this right now. And one of the big key, computing is part of that, but another big key in doing computing in space is going to be the memory technologies and storage. And there's particular challenges that some of these technologies face, or particular environmental challenges that may lead us to using different types of technologies than we use on the Earth. We'll talk a bit about beyond where we might go. I'll talk about that this IEEE Space Tech Initiative as well as a summary. So that's my talk. Let's first talk about some of the challenges and opportunities here. So one of the big enablers here is the fact that the cost of, with the development, especially of competition and private space transportation, the cost of bringing things into space, especially inanimate stuff where you don't have to deal with additional complexities with humans, have plummeted from about $22,000 per kilogram US dollars in the Apollo program back in the 1960s and 70s to about 2,720 kilograms of SpaceX Falcon 9. But in the not too distant future, especially with larger space vehicles, reusability of components more components become more common. These costs are projected to about 100 kilograms, $100 per kilogram. And you can see there's a chart there that sort of gives you an idea how that might happen, or the course of time in which that happens. So we're not too far off from a much less expensive space transportation. Let's see. Oh, there it is. So it costs a lot of energy to get into orbit. Much less when you're there. You can actually use. There's possibilities, and I'll talk about that, of lower overall thrust devices, but continuous devices that could be used to, especially with inanimate objects, to a very effective transportation once you're in space. For instance, with the Artemis 2, over 700,000 gallons of propellant was used to escape the Earth. But once in space, moving even a big vehicle like that relied upon efficient small maneuvers, and also using gravitation assists, slingshots around the sun, things of that sort. So getting off out of the Earth's gravity well takes a lot of energy, of course, but it doesn't take so much energy to move around once you're there. So getting things going in space takes some energy and investment. But the interesting thing about that is that once you have things there, if they stay there, if they grow and leverage off that, the costs go down an awful lot. And for instance, to talk about the propulsion systems, we can use lower energy, lower immediate thrust propulsion systems for movement once you're in outer space. There's things like ion thrusters, like that shown to the right here, which are high efficiency electric engines. They use electromagnetic fields to accelerate ions, that's charged atoms, and they produce low thrust, high velocity propulsion. They consume about 90% less propellant than chemical rockets. So they're ideal for long duration deep space missions, for example. Solar sails, another technology people are talking about, actually using the solar wind in order to propel things in, for instance, in the solar system, especially for non-time critical equipment only travel, for example. And lasers have also been proposed to provide more effective solar sail technologies, where you're using more intense and directed beams of energy to help propel things, and even for long duration space flights, potentially even to other stars. People have talked about that. In addition, vehicles meant for use only within space can be built very differently than those designed to endure travel from and to the Earth's surface. You don't have to worry about, the stresses and strains of takeoff and landing, the thermal environments and things of that sort. They just stay basically in within you have challenges in terms of temperatures and things of that in space, but a lot less than the mechanical kind of issues that you have to worry about. So you can maybe build them differently, especially, again, if you don't have people on board. So communications, in which I know you guys are connected with here, there's interesting things going on there. For instance, laser communications, direct laser communication between things, is being talked about as a common element, actually, in some of these satellite sort of micro constellation satellite-based communication or computing communications networks. There's Artemis 2 had this hello world downloaded to Earth using lasers, and transmitted about 100 times faster than traditional radio, they say. And it's also being used in satellite networks like Starlink, laser communication. There's a European company called Astrolight that I found out about, developing a compact 10 by 10 centimeter low-cost systems that can be integrated into satellites across different operators and applications, for example. One of the issues we're dealing with is that everybody is doing things in outer space right now, and there's a lot of abandoned hardware in space. According to the European Space Agency, there are about 54,000 space objects in Earth orbit. Their total mass is about 16,200 tons. The estimated fragmentation events that have occurred are more than 660. Many of these objects eventually burn up entering Earth's atmosphere, but many don't. And if they hit each other, they create more fragments and it gets more and more debris into space. So, and with current launch schedules for all these companies and countries launching things into near Earth orbit, for example, in particular, this number will increase enormously. So reaching or going beyond Earth orbit can become more challenging in this case, and so we need to think about what we do about all that debris in space. We need perhaps there's a startup opportunity for garbage collection in space. How do we harvest these things? Of course, you could drop it into Earth's atmosphere and burn it up, but that does create some degree of pollution, or at least some changes in the environment, not a huge amount. But you've already got this stuff in space. And one of the things I've always thought, if you got something up there, better to keep it up there, put it someplace where you can utilize it later on when people actually start manufacturing and using resources in space themselves. So I think there's some potential opportunities there. There are also, as you folks probably are aware of, things like the planetary internet. Vince Cerf pioneered the concept of doing that many years ago, that would connect different types of space assets to each other and ultimately connect those assets with the Earth. So the interplanetary internet is different than internets located on the Earth. It's envisioned as a store and forward network of internets that's often disconnected, has a wireless backbone fraught with error-prone links and delays ranging from tens of minutes to even hours, even when there is a connection. And participating communication nodes in an interplanetary communication system will keep changing over time due to constant motion of the various bodies that you may be engaged with. The routes of the interplanetary communication then have to be planned and scheduled rather than being opportunistic and whenever you want to do it. So so that's part of this reason to do the store and forward, of course. And because the delays in relaying messages over the vast distances of outer space, local systems must have sufficient autonomy to be able to make real-world decisions. This processing and store and forward interplanetary networking will drive a need for data centers in space, for storage and memory in space, and having these things close to the equipment that they're managed, so that you can reduce that latency issue. So that leads us to the concept of why we need to think about data centers in space. So physical AI, that's whether it's autonomous or semi-autonomous robots, that's usually what people are talking about with that. It's been a big deal with companies like NVIDIA, pushing for that. And also a lot of people talking about using this autonomous vehicles, robotics in the home, manufacturing things as well. But it also enables us to do things in space, things that can stay in space. They don't require the same kind of resources that humans would require there. And these devices, robotic devices, could create infrastructure and also harvest materials for the further development of outer space. Again, launching stuff up there and then having it stay up there and do things. Much of the future space developments, I think, will be done using robots and AI. It's cheaper and also less risk to humans. And that's going to require local data processing and communication infrastructure to reduce the latency, enable more real-time control and response as things develop. So I think we're going to need data centers of some kind in outer space and a communication network to connect these data centers to the things they need to connect to and interact with in order to enable the development and the humanization of outer space. So I asked AI to generate me an image. It came up with this thing. And the basic idea here is that cheaper transportation in space makes it easier, less of an economic burden to do more things in space. And that can include mining asteroids, for materials, collecting, or say the moon. You know, people talk about looking for helium to help with fusion reactors from the moon. Collecting using solar energy, setting up new and more powerful telescopes, including very sensitive gravity wave observatories in space, making factories for the production of goods, space infrastructure, new space vehicles. And recently, the word has leaked out in the last week or so about SpaceX's Starfall program for delivering goods manufactured in orbital factories to the Earth. So these scientific, transportation, industrial systems will likely be highly automated, and they'll be an example of that physical AI. And they'll need local as well as distributed data centers and space-based communication networks to connect them and the Earth. So in addition, energy constraints and issues such as water cooling are one of the biggest challenges of building Earth-based data centers for large AI deployments. In outer space, there's abundant energy available from the sun, of course, if you collect it, for doing all kinds of things, including AI, and there's various types of high-performance computing. Now, you have issues still of dissipating heat, especially if you don't have convection. That's mostly going to be radiative heat, so there's going to be a lot of radiative structures built into these systems. But you know, it seems like something that we could do. And these space-based data centers be able to communicate directly, although with some latency and potential delays, to multiple Earth locations, creating new accessibility for extraterrestrial cloud resources as well. And I know that a lot of the people talking about these data centers in space are talking about as being, you know, providing new cloud computing resources. I think what's going to really drive it is going to be they're used for things that are going on in space. So some examples of things that have been happening here. A bit of history. Back in 2016, there was a U.S. startup called Cloud Constellation that wanted to build an array of equatorial, low Earth orbiting data center satellites in order to provide a space-based infrastructure for cloud service providers so they could better serve corporate and government clients. The digital storage would be used in these orbiting data centers was to be solid-state drives. In December of 2022, Lone Star Data Holdings announced that it wanted to build a data center on the moon for backing up the world's data and also supporting lunar edge processing needs. 2025, last year, was a really busy year for outer space data centers and the digital storage technology demonstrations in these data centers. In January of that year, Flexential, a major data center provider, and Lone Star Data Holdings out of Texas, said they would collaborate to support the then upcoming launch of Freedom, its second project to create a data center on the moon with Intuitive Machines' Nova-C lunar lander, which was to be launched on a SpaceX Falcon 9 rocket. About the same time, another lunar lander embarked on a journey to the moon carrying NFT tokens, non-fungible tokens, and a significant piece of historical data encoded in synthetic DNA from startup Iridia. I think it was actually Leroux cave paintings, if I remember right. Pictures of that. This was encapsulated within a monument that was supposed to symbolize humanity's achievements and carried in LifeShip's Luna payload on the Dragonfly Aerospace Blue Ghost lander. You can actually see a picture of that here sitting on the moon. And this monument is projected to endure for a millennium because of this DNA storage on from Iridia, at least the data lasting for a long time. And of course, there's not a lot of environment on the moon to destroy things. In some more stuff in September 2025, Axiom Space and SpaceBuilt Incorporated announced a collaboration to bring optically interconnected orbital data centers infrastructure to the International Space Station by 2027. And this infrastructure would include an optical communication terminal by Skyloom, storage and other hardware from Phison Electronics, which makes solid-state drive controllers and solid-state drives, and microchip technology, which makes various controller and other electronics. This system is intended to allow satellites, other spacecraft in low Earth orbit, and astronauts and researchers to store and process data and run AI workloads in cloud computing applications. And this builds upon results from the Axion Data Center Unit 1 delivered to the space station in August of 2025. In November of 2025, NVIDIA-backed startup StarCloud launched an NVIDIA H100 GPU into orbit on its StarCloud 1 satellite. So while in space, the StarCloud satellite was able to train and run a large language model using Nano GPT running on the complete works of Shakespeare. The model was then able to answer queries in Shakespearean English. It has also been running and querying responses using Gemma, an open language model from Google based upon Gemini. The next satellite launch will include several NVIDIA H100 chips from this outfit, And integrated Video's Blackwell platform is scheduled to launch in October of 2026. It'll run a cloud platform from cloud infrastructure startup Crusoe. StarCloud plans to build a 5 gigawatt orbital data center with solar and cooling panels measuring 4 kilometers square. They project these satellite data centers would have a 5-year lifespan given the expected lifetime of the NVIDIA chips in that environment. Blue Origin also plans for a satellite constellation data center with its project Sunrise. Also in 2025, in October, Google unveiled an initiative called Starcatcher that aims to put solar-powered satellites into space with Google's tensor processing units. Another company, Aerolux, announced a target to deploy an orbital data center satellite in the first quarter of 2027. More recently, an outfit called Cowboy Space out of San Carlos, California, wants to begin launching 20,000 satellite orbital data center constellation by 2028. So, and by the way, the SpaceX was talking about up to 1 million satellites in a data center constellation. So the stars, if you will, appear to be aligned on creating some kind of extraterrestrial data sphere. So there's some things in IEEE recently on this. This is from February 2025. Talked about the Lone Star Freedom Data Center payload, which I did mention before, with this Intuitive Machines mission lunar lander. So it contained this mini data center, weighed about 1 kilogram. You can see a picture of that black thing there. It contained 8 terabytes of SSD storage. So not very big, but it was like supposed to be a platform to find a proof of concept. Now the problems, they actually had problems with this lander, and they've had it a couple times. I think part of because it's kind of top heavy. And so if it lands on the surface of the moon, which it did with an angle, it actually fell over and never wasn't able to carry out its mission. February 2026, there was another Spectrum article. It included this vision of a server farm satellite with 1,000 square meters of photovoltaic panels generating 240 kilowatts. Cooling done by circulating a fluid around the processors and into channels to the radiator panels. And the satellite was these satellite modules would have 2 racks of GPUs, each with 72 GPUs in a rack. And to create a gigawatt of processing power required about 4,300 of such satellites. So give some idea of just the size of these things. More on that, some of the richest, most powerful people in technology are backing data centers in space, including Elon Musk, Jeff Bezos, Jensen Huang, Sam Altman, Google CEO Sundar Pichai. Aerospace engineer Andrew McCallop, again, this is IEEE Spectrum in February this year, estimates the cost of an orbital data center described in the last slide, the one I just showed you before this, could be about 3 times that of a comparable terrestrial one using modern radiation-resistant technology. Now, that is a more expensive data center, but it can serve needs that terrestrial data centers can't. And the biggest thing about that is that's down from maybe 50 times or more expensive doing such a thing in space in the not too distant past. So again, it seems like this is something that's probably going to be able to be, people are going to start doing. So let's talk about some of the infrastructure, some of the technologies needed to make this possible, in particular, memory and storage in space. So memory and storage critical, of course, for data collection, retention, and processing, important for AI, but everything else as well. But outer space exposes electronics to challenges such as radiation, a high radiation environment, both ionizing, non-ionizing radiation, if you're outside of the Van Allen belt, can cause soft or hard permanent errors, and smaller lithographic semiconductor devices may be more vulnerable to these kind of errors. There's extremes of heat and cold and the lack of convection to remove the heat. And for applications launched from and landing on Earth, shock and vibration from launch and landing can be issues. For some applications, there can be power constraints or related heat dissipation issues as well. And temperature regulation may favor computing and processing in environments with higher surface area than volume. Hence, we might, a constellation of small systems rather than larger one, which has a larger surface area and therefore can radiate better, maybe the major components of an outer space data center, hence the creation of these constellation systems. Over the years, various memory and storage technologies have been used in outer space. Hard disk drives have been used in some space missions and in laptops in the ISS in the past. Today, there are hard disk drives that are actually hermetically sealed, so they can presumably go in the radiation or in the environment of space, and they would still operate because they're filled with helium, hermetically sealed, so the heads can still fly above the disks. SSDs are a more popular storage technology for outer space, particularly because the solid state and they have more shock resistance and issues like that. But they have to have a radiation hardened controller and special error correction to safeguard data. In fact, even with hard disk drives, the vulnerability there is not going to be in the magnetic technology from the radiation. It's going to be from the electronics that control it. DRAMs face significant challenges in space because they are very susceptible to radiation-induced hard and soft errors. And there's several non-volatile memory technologies can be used instead of DRAM for space-based memory. They include magnetic random access memory, resistive memory technologies, and ferroelectric random access memory, which are not that sensitive to radiation. So there's a company called Infineon out of Germany, which acquired Cypress Semiconductor in 2020. And with it, it acquired the memory business they have. And they have non-volatile memory technologies. They have NOR flash, but they also have ferroelectric random access memory devices that could be very appropriate. And in fact, they sell them as radiation hardened electronics. So that's one company that's participating in these areas. Another company called Everspin makes magnetic random access memory, and especially STT MRAM, that's spin tunnel torque, stores data using magnetic states rather than electrical charge, which can be sensitive to radiation. That makes it resistant to radiation-induced errors and immune to single-event latch-ups. So Everspin, there's a number of companies in these areas. Everspin is the oldest standalone MRAM enterprise. Says their MRAM can replace slower and less reliable flash memory and SRAM for tasks like boot code, data logging, and FPGA configurations in satellites and in other space systems. MSA components offer the space-grade non-volatile memory based upon MRAM from Everspin. Now, in addition, there's other companies that are in the space of the MRAM space for space applications. Avalanche Technology, in particular, has been advertising their MRAM for use in aerospace applications. They have a VNX Plus ruggedized storage device with up to 8 gigabytes capacity for both aerospace and low Earth orbit applications. They actually wrote a white paper on using MRAM in data centers in space on these constellation data centers for large satellites and small satellites. And the company is designing a moon drive for deep space applications, currently up to 1 terabyte, but it's in a 6U form factor, so it's kind of large. With the company's higher density 2 gigabit and planned 4 gigabit devices, they can reduce the size of a 1 MRAM SSD. And the figure below from that white paper outlines an array of small satellites, or the figure to the right, actually, create a network of high-performance data center nodes. So this network connects smaller constellation satellites and larger data center satellites with MRAM acting as a multi-image bootloader, a compression, decompression buffer, and as a storage buffer, or even as the main storage, or complementing a larger storage device. In March of 2023, Kioxia America, a manufacturer of NAND flash and SSDs, announced its participation in the Hewlett-Packard Enterprise HPE Spaceborne Compute 2 program. In this program, Kioxia SSDs provided flash storage in HP Edgeline and ProLiant servers in the test environment on the ISS for conducting scientific experiments as part of a greater mission to advance computing and reduce dependency on communications by providing local storage as space exploration expands. So this photo here is an SBC2 HPE server. Taiwan-based SSD controller and storage product company Phison announced their SSDs had been certified to be used in lunar data centers in 2022. Phison supplied the company's Pascari enterprise-grade SSDs to deliver over 1 petabyte of storage to the AXODC node on the International Space Station. The Pascari SSDs used for space applications are modified from their general enterprise Pascari SSDs to work in outer space. The D200 series modified SSDs used in the Lone Star lander we talked about before can operate in extreme temperatures from minus 280 Fahrenheit to 260 Fahrenheit and are radiation hardened to withstand cosmic radiation. They're also built to endure launch vibrations, high G-forces, and a vacuum environment. In addition to the ISS and various lunar data center missions, Piscari SSDs are being used on the Mars Perseverance rover. Iridia, talked about a little bit about them before, collaborating with Arweave, an open source protocol for permanent data storage, and the ASI Alliance on the creation of the cryptocurrency tokens stored on that synthetic DNA on that Dragon Aerospace Blue Ghost lander. Following the spacecraft's landing, the public keys for the tokens were shared on the Iridium website so people could see and potentially interact with these lunar-based assets in some way. A 5D memory crystal from a company called S-Photonics, which is actually recording in the volume of a quartz crystal recording information, containing art and technology created by Moon Mars Museum, was launched as part of a Space Renaissance for All payload on a SpaceX Falcon 9 rocket in June of 2025. It's included Chauvet, they were the Chauvet cave paintings from France that are over 32,000 years old, images of that. They were etched into the quartz structure with representational artwork on the exterior. And so that spacecraft is scheduled for a lunar landing in early 2026. As Photonics said that a different 5D memory crystal was part of Elon Musk's SpaceX Falcon Heavy 2018 launch, containing a copy of the Isaac Asimov Foundation trilogy, placed into the glove compartment of the red Tesla Roadster that was launched into space at that time. So, where do we go from here? Ad Astra, to the stars, to the future of space. Digital technology will be a crucial element in the exploration and industrialization of outer space. And radiation-hard digital storage and memory will be essential to carry out tasks with a high degree of automation required for these activities. If last year was any indication, data center developments in Earth, and seem to be this year, development in Earth orbit and on the surface of the moon is accelerating to support these activities. We may see large space data centers in Earth orbit in just a few years, assuming we can deal with the space debris we talked about earlier, and international rules on the use of space, which are kind of pretty loose and undefined right now. As humanity moves beyond the Earth to use the vast energy and material resources available in our solar system and someday beyond, we're going to need processing and communication technologies that support a far-flung extraterrestrial society. So I foresee a day when there are many more data centers in space than on the Earth, when more materials and energy used by humans are harvested and used away from the Earth than on the Earth, and goods can be delivered to the Earth from space. And with new technologies for processing, computer processing, memory, and storage developed and manufactured away from the Earth. Technology, I think, will be the means for us, even as we spread out across the solar system and beyond, to stay connected and hopefully build a sustainable world, provide new opportunities to achieve happiness and plenty. So I think technologies that people work on in computing, processing, memory, and storage, open space to human development, plus all the energy-based technologies. That will create demand for new types of food technology to support humans in space, to deal with radiation and other hazards. Will we live in tunnels, or are there other more open options? For instance, this picture from back in the 1970s, Gerard O'Neill's space habitats. Eventually, this might include terraforming other worlds, such as Mars. So in closing, I have a report that I do with a colleague on new memories, which these new memories you talked about that are radiation resistant. It could be useful in space. There's information on that here. Also, I mentioned this at the beginning, and this group in particular might be interested in this, is the Future Directions Committee of IEEE, and I know your group spun out from that, is funding an initiative on space tech, which probably officially funded. It's as a special project right now, be officially funded at the June meetings. And topics that are being addressed in this include space mining and manufacturing, space robotics and automation, long-term human habitation, debris migration, or mitigation rather, space sustainability, non-terrestrial communications, and space technology standards. So in summary, lower costs for space transportation are enabling the humanization of outer space for us in our artifacts to do more stuff in more places. And we will increasingly come to depend upon resources from space, I believe. This will be particularly using physical AI, semi-autonomous robots needed for various types of space development. And that will drive demand for data centers in space. And building those data centers requires new technologies for processing, memory, and storage. And there are a lot of well-funded space data center projects currently underway. It looks like this is a going thing. And those developments will create outer space as a new human frontier. So I got a few pages of references here. And that's basically my talk. And I'm open to questions or comments, thoughts, and I will quit sharing here if you guys are still there.